this minute.
Okay, guys, so settle down, please. Next talk, Alexander will talk about database exploration, so please.
Okay, so my name is Alexander Dyke. I usually go by Alex, but emails you'll see Alexander H. Dyke. Anyway, I'm working within the network services team here at Red Hat. We focus on my group within the group focuses specifically on core kernel networking and trying to get it to go as fast as possible. So to that end, this presentation is meant to help you get an idea of why when you have maybe like a customer come to you and complain the networking's not fast enough, I'm doing this one flow and it's dropping packets, what's actually going on? So as far as an agenda, first I'm going to try to explain what the problem is. You know, why is it so difficult to receive packets at line rate? Then after that, I'll give kind of a brief overview of where some of the problems lie, some of the issues we're trying to address, and then how we're going about trying to address those issues. Specifically, there's been a lot of work done over the last year, some by other members of the team, some by myself, and there's still a lot more work to be done, and I'll try to touch on that briefly too. So, why is it so hard to receive at line rate? Well, it depends on what your definition of receiving at line rate is. Right now, the current network stack, if you break out netperf with just a standard bulk stream, large packets, you can do one core, 10 gig line rate, no problem. Now, if you start talking about 60 byte frames, it starts to become a different story. With 60 byte frames, you only have about 24 bytes of additional overhead per frame. So you're looking about 84 byte message that's passing over a 1 gigabit, well, either a 1 gigabit or 10 gigabit media. That's what's currently available right now. And so you're looking at about 125 megabytes per gigabit, or with 84 bytes per packet, which gives you roughly 1.488 million packets per second. Now, in some scenarios, that rate's doable. Others, it's not. But that's only 1 gig. Now we start getting into 10 gig, and that multiplies everything by a factor of 10. It makes things significantly more difficult for us to try to achieve line rate, especially if you're talking about trying to do it with just a single processing core. I included a small video here, kind of help visualize the issue. So now imagine Lucy and Ethel here are a couple of our processing cores. Their simple job is to take these frame headers that are coming across this line here, and encapsulate them in a tunnel header, let's say. Now, the problem is the customer has a very specific requirement. They want the packets to go across, no frame drops. You'd be surprised how often this is a requirement. Nope, you can't have any frame drops. Whatever you report as your rate, no frame drops, or else forget it. Well, you start out, packet spacing is pretty good. Maybe you start at the beginning of the TCP flow. It's a SYN, an ACK, one or two. Then things start speeding up. Next thing you know, you're starting to have to, crank the CPU up to 100%. Okay, we're still good. And then things still speed up some more. And then the buffering starts. The problem is, once you start buffering, then you start having caching problems. You can't handle things fast enough. Next thing you know, packets are going sideways. They're going out into the L3 cache. Oh, no, I need that back now. Okay, no, I got to process this. And it gets faster and faster. Let's see, and I think right about, well, we got something eating packets there, so. But yeah, before long, you end up, there goes a packet. Okay, test results are no good anymore. You dropped a packet. And the test's still going, basically from this point forward, it just gets really ugly. Yeah, they're wrapping up the packets here really fast, but yeah. Buffers blown, stash the data where you can, but not going to do you much good. And even if you were able to fake the results and say, okay, yeah, we did it, then the customer's going to come back and say, yeah, okay, let's go a little bit faster. So as I say, it's basically a matter of timing. When you start looking at how much time we actually have to process each packet, for 1 gig, We got 672 nanoseconds. That's an eternity. We can just about handle that with small packets. Actually, the testing I've been doing recently, yeah, that's not even a challenge. I can do that. But then you start getting down to 10 gig, 67.2 nanoseconds per packet. That's not very much time, especially, and then they're already talking about 100 gig. That gets us down to 6.72 nanoseconds per packet. If you think about that in light, I'm trying to think, like light nanoseconds, basically a light nanosecond is about a foot. So light will have traveled about 2 meters in the time it takes us, or the time that it would take us to process a 100 gigabit 64 byte packet. You think about that, that's kind of getting ridiculous. That means, if we're running around inside the processor, we can only have the electron move 2 meters in the time it takes us to process a packet. And you start to see it in other things too. So for example, the L2 cache latency on an Ivy bridge is 12 cycles. It doesn't sound that bad, except for each nanosecond on, like in the case of my Ivy bridge, it's 3.4 gigahertz, so it processes 3.4 cycles in that 1 nanosecond. So you do the math, 12 cycles divided by 3.4 cycles per nanosecond. I've only got 3.5 accessing the L2 cache. This isn't a miss. This is L1 cache miss, L2 cache hit. Takes me 3.5 nanoseconds. So if you're talking about trying to do 100 gigabits per second, if I'm trying to do it on a single core, then what I'm looking at, I can take 2 L2 cache hits before, time's up, I'm done. So 100, right now with current CPUs, 100 gigabit per second, if we're going to even try to do small packets, we'd be looking at most likely saturating all the cores on a system with many, many cores. And hopefully it all scales. So from there we have to start trying to figure out, what is it that's slowing us down? So if you take a look at the kernel from probably like 6 months ago, the range could vary anywhere between microseconds to process a packet down to, like in my test system, I got it down to about 300 nanoseconds. So yeah, we can do 1 gig, but you start trying to do 10 gig at line rate, it doesn't quite work out. You come out somewhere a little over 2 million packets per second. And so when you start looking through the profiles, you start seeing certain patterns pop up. One of them being if you're working with a hardware NIC, you have to go and access the device, usually via memory mapped I/O, which means an access to the PCIe bus, typically on the device. This has some very expensive costs to it. Doing a read over PCIe, yeah, if we were doing that, forget it. We're done. But the fact is, most drivers now don't even bother with that. They just allow, enough logic in the hardware to deal with things like masking the interrupts on their end. So all we have to do is enable them after the fact, provided we're not busy enough to do, to need the interrupts still disabled. Like if you look at some of the old 100 megabit drivers and such, they used to do things like, I'll go read my queue register or whatever to go figure out where you're at, where the hardware is at in the queue. If we did that, forget it. You're done. You can't even hope to achieve it. The only problem is we still have to do MMIO access for one thing, and that's to notify the hardware that, there's packets available now. And so what ends up happening is we usually end up making a MMIO write, which is this write-L call, into the hardware to notify it of the tail update. Well, that should be more or less asynchronous, something we can just put out there and it's done, except for the fact that there's things like barriers floating around in the system. And the barrier state, you have to complete all writes to non-coherent memory before you can proceed any further. Side effect of this ends up being one of the biggest expenses for most systems if you're doing just a NIC-to-NIC test shows up in kind of an odd way. Specifically, actually I better cover one other thing here first. Another thing that can act as a barrier in most systems is atomic operations. So anything that does like atomic inc, atomic deck and test, compare exchange. So pretty much any of the atomic ops or spin locks or any of that also act as barriers. So you combine that with the first item. Well, barriers in and of themselves slow things down. But then you combine them with an MMIO, and it's like a train wreck, basically. You sit there and you watch, and all of a sudden one spin lock eats up 120, 140 nanoseconds in the system. Eats up something like 30% of your CPU time for processing packets. That's all just because of the MMIO and barrier effect. The other bit in all this is, so we're processing a 64-byte packet. Before we can even really get to the 64-byte packet, we have to have somewhere to put it. So we allocate a page. Well, the page struct takes up one cache line somewhere. Well, there's another 64 bytes. And we have to allocate a receive buffer, or SK buff, so that we can eventually hand this off to either a socket or another net device. Oh, well, there's another 4 cache lines. Oh, except for the SK buff also points into what's called the shared info. And there's a couple more cache lines. So now, so far, just to process our 64-byte packet, we've got an extra half dozen cache lines that we're having to touch. And then it gets worse. Well, we've got to route the packet somewhere. How do we know where to route it? Well, we have to go take a look up in this fib table thing. Okay. Well, how many cache lines is that? Well, it depends on the number of addresses you have. Ends up usually being something on the order of log n. So say you have like 200 addresses on a system, 8 memory lookups. Oh, and it's maybe 2 cache lines per lookup node in this tree, so another 16, assuming it's a local address. There's also a routing table for the non-local addresses, which might be another 16. So it just ends up being this thing that kind of snowballs and collects more data as it goes. So before long, you start running into things like memory limits on the system, just because you're receiving a 64-byte packet, and it has to add so much data just to get to the other end. So how do we start addressing some of these problems? Well, the first step, and this is actually something that occurred just a little before I joined the team, actually. So in order to try to resolve that MMIO issue, one of the things we came up with was coalescing MMIO writes over multiple frames. So in scenarios where, say we have that buffering going on, where in the transmit layer we know we have 5 frames to send because, well, we weren't able to get to those because the ring was full earlier. What we can do now is we say, okay, we've got 5 frames, we've got the device ready. We just hand it 5 frames outright instead of handing it 1 frame at a time, which is what we used to do. And then we only have to notify the hardware once. So now suddenly, instead of spending 100 to 150 nanoseconds per frame, well, now we only have to spend it per 5 frames or 16 frames, however much we've backlogged while we were waiting for the ring to become available. One of the spots where this actually became really apparent was with the packet gen test. So for those of you that aren't aware, packet gen is a very simple tool. All it's meant to do is generate 1 frame and send it over and over and over and over again to the network device. So ideally, you're not doing a whole ton of memory allocation, all that. It's just transmit as fast as you can. Well, before these patches went in, a single core averaged about 7 million packets per second. That's about all you could do. After this patch went in, you could specify the option to burst a certain number of frames. I'm trying to remember the exact number, but somewhere around 32 to 64, suddenly you could hit line rate. Just done, go. And it would just zoom along. And so actually this came in handy for a couple of reasons. First, it shows that, yes, MMIO was a big expense on the hardware. The other item is, well, now we have a traffic generator that we can use that does line rates, so at 10 gig. So let's just use that to, be our test bench, so to speak. So I actually have a VM in my test setup that has just 1 CPU on it. That's my traffic generator, generating 1 pattern at line rate 10 gig. So once I had that, I started looking around, seeing where else we had little spots where we were slowing down. one of the spots I ended up finding was that in a number of areas we were using barriers that were far more restrictive than they needed to be. And it was just because of the semantics of things. Within the kernel, we have the concept of memory barriers and SMP memory barriers. The difference being SMP memory barriers only really applied when you're in a multi-CPU situation because you had contention between the CPUs. Well, in a way, another device in the system could act as another CPU. So in the case of many drivers, and specifically here, I was working mostly with the Intel drivers, but most drivers have a setup such that they have receive descriptor rings that describe where the data goes, and then they have the data itself from the packet. And so you generally want to ensure ordering so that if you check and see if this descriptor is ready, okay, now I can go read the data. Well, to that end, we had to have a memory barrier in between the two so that you guaranteed that, okay, yes, data's ready, and then read data instead of read data, it's ready because, it might not have made it here before you read this one. So what we ended up doing, excuse me. So what I ended up doing is looking into a couple things. And I originally started out basing things off of some stuff the RCU guys had done. Specifically, there's what's called load acquire and store release semantics. What that ends up meaning is that, I want to guarantee, in the case of store release, I want to guarantee all writes are completed before I complete this next write. Or load acquire is I want to guarantee all reads are performed after I perform this read. Well, looking through that, what I ended up finding is on x86, it was a barrier call in GCC, which ends up just coming out as nothing. And I sit there thinking about it, it's exactly the same use case we have here, where it's essentially, before I can acquire the data, I need to read it and make sure it's done. And so what I ended up doing is I actually submitted, originally it was I think DMA acquire, DMA release, something like, or no, I'm trying to remember. It's like device acquire, device release, something like that. It basically went back and forth a few times, and then it was coherent, RMB. Finally ended up settling on DMA, RMB, and DMA write memory barrier based on a suggestion from Linus in terms of the naming. So that was basically the last comment he had on my patch. He hated the name of the function, but the rest of it was fine. So I just renamed the functions and got the patches applied. But yeah, so basically with the barrier removed, we saw another 7 nanoseconds gain just from the fact that we weren't having to stall out the pipeline because the memory fence instructions just get really expensive, especially when you're trying to process packets at a very high rate. So where else can we save space? Well, as it turns out, there's a lot of other spots within the kernel where we're having to do I'm trying to think. Basic serialization of things in order to prevent accesses at the same time. So one of the other spots is we had this function called netdev_alloc_frag. What it was there to do is to basically break a page up into multiple smaller pages to be used for receive. The only thing is, the way it was set up is they had it wrapped in local IRQ save and restore in order to prevent us, from accessing it at the same time and causing contention on the system. The thing is, though, in the use case for most network drivers these days use a interface called NAPI, or New API, which it's meant to push the network receive processing into a single soft IRQ task. And so you'll end up with all the network receive functions serialized within this soft IRQ task. So they won't actually contend against each other. So I thought about it and it's like, well, why do we need to prevent contention if we can't cause contention anyway? So a simple solution for that is to go through, and I came up with my own function that had its own separate per CPU area and just remove the local IRQ save and restore. Just by doing this, there's another 11 nanoseconds we could cut out of the path, since we now don't have to restore flags and whatnot after trying to allocate part of a page. The last bit, which I've actually been working on now for the last 2 months, is the fib table lookup problem. Specifically, the fib table, or actually fib tree, ends up being a set of tree structures. And for those that aren't aware, it's essentially a modification to a binary tree that can be dynamically sized. But anyway, what you end up doing is you walk yourself down this tree trying to find the best match for your source IP address or your destination IP address, just to try to figure out either where you came from or where you're going. Specifically, what ends up happening, though, is the process for this was really complicated. And so, unfortunately, a lot of people, I don't think, really looked much at this code. And so, there's the general assumption, well, it's in the kernel, it's probably been optimized already, I can probably let it go. I started digging into it, and I kind of started pulling my hair out in spots. I'm like, why? Why are they doing this? And then there was a pointer to a document that was their original source material. Turns out the original implementation for this was written in Java and ported into the kernel, which explains why I started seeing a lot of functions like leaf new, tnode free, leaf free, and some list manipulation stuff, and casting that made no sense because there was like 3 different structures and they were casting it back and forth everywhere because I guess that was their way of implementing it as a class and then as like subclass and such. Anyway, so going through the tree, I started to realize that there were spots that could be optimized all over the place, little things that were overlooked. One of the biggest was the fact that, so when you do this longest prefix match, you have to walk yourself down the tree and then walk yourself back trying to find the closest match. That process actually came out roughly as an O(n) squared algorithm. So the bigger the tree got, the slower it got by like orders of magnitude. So in my test, I actually created a tree that had a depth of, I think it was 7. And with that, a lookup that normally takes maybe, I'd say 50, 60 nanoseconds with a very small tree took about 1 millisecond. So that's like 1,000 nanoseconds right there. So I started looking through and found various spots, and there's like, I think I'm 20 patches deep at this point and have another 20 yet to submit. But essentially I'm able to go through, and I cut it down to an O of n lookup. The big advantage being, obviously I'm able to take the 1 microsecond lookup and cut it down to 140 nanoseconds. The areas I still have to work on, though, this still consumes 2 cache lines per lookup. I'm thinking this can be massaged such that if you rearrange the data a little bit, it's a little bit hairier for the insert and the delete, but the lookup time will come down to 1 cache line per lookup if I push the key data and the pointer to the next object into the same cache line. Because that's basically the big problem right now. Each node in the tree has an array of pointers that can go on forever. So you do some key work over here, and you go over here to go fetch this pointer, and your next level down you're doing the same thing. So by pushing the 2 together, having it be a pointer to an array instead of an array of pointers, I can actually cut that down to 1 cache line per lookup. The results are actually pretty good in what I've seen so far. I just have to sort out some RCU bits still. So I think I've got it down to about 90 nanoseconds for my worst case now. And the other one is the fact that there's a structure in there. I think it's a container of some sort. I'm not sure what the point of it was. Essentially all it's there for is it contains almost the same data as all the objects that are underneath it. The only difference is the leaf info contains what are a list of what are called fib aliases. And the leaf info contains like 1 byte of data about the fib aliases, which is essentially the prefix length. And it happened that the fib aliases had a free byte available in all of them. So I'm like, okay, just move the prefix length down and chuck this structure. And I had to save myself a cache line in lookups. So with all of that, it ends up being a pretty significant savings. If nothing else, the stuff that's in the kernel right now with the netnext will at least address it down to 140 nanoseconds. So it gets it down to O of n of lookup, and then basically I'm just cutting that time in half with the follow-on changes that are needed. So, what's left to be done? Well, like I said, I still have some more work to do on the fib table lookup. Most of that's just going to be dropping cache lines where I can. The other big item that ends up showing up, so like I mentioned, build SKB is this big, ugly structure that, for a 64-byte frame, we're allocating 5 times that, well over that actually, but we're touching 5 cache lines within it. in order to make everything go. And if we can somehow cut that down, that'd be a significant savings. Because just initializing the memory for that takes 20 nanoseconds, because there's a big memset 0 in the SK buff that has to happen, and that takes 20 nanoseconds. So we need to be able to get rid of that before we're going to be able to get anywhere near 1 gig or 10 gig line rate. And the other item that shows up is a mem copy. That I'm not so sure we can get rid of, though. But there might be some tricks we can do to reduce that time. Specifically, the mem copy is there to copy the data, the header, out of the data field of a page and into the SK buff. The reason for doing that is otherwise we have to go back to the atomic stuff and take a reference to the page. So right now it's like, okay, mem copy or atomic operation, and mem copy doesn't flush pipelines. So right now I lean towards the mem copy. And then there's some other work ongoing. One of the people on my team, Jesper Brouwer, has currently been working on with Christopher Lambert, to do a batch allocation for the SK buff head. So by doing this within the like slub allocator, for instance, there's a compare exchange. I think it's a compare exchange double that has to happen in order to pull an item out of what's called the free list in order to go grab a SK buff. The problem is that ends up usually being another locked operation, so it shows up as a hot item in our list. And so what I end up doing, or what he's looking at doing, is instead of allocating one at a time, well, you know, in NAPI we do 64 buffers in a single process, so allocate 64. And we take that hit once and push that through the soft IRQ handler, and hopefully that'll help coalesce some of the overhead for that. For those that are interested, I guess there's a set of patches that went out to test that, and there's the URL. And other than that, it's just a matter of trying to figure out where we can still cut costs. The receive path, one of the biggest things is the fact that we have to process packets one at a time. So there's other tools out there, or other SDKs such as DPDK. Some of you might have heard of it. One of the things it does in order to get around a lot of this is it doesn't bother with this one at a time processing. It'll do like 8 packets at a time in order to push them through the stack all at once. So we're trying to see where we can get away with some of that. So like, for example, the transmit more, which I mentioned earlier, is doing transmit batching, so we can take advantage of that. But it only works in so far as the device has to be backlogged. If we're not moving fast enough right now as is, we can't get the packets from the receive side to the transmit side to backlog it. So we have to find some means of triggering some coalescing on the receive side in order to make it flow all the way down to the transmit side. So otherwise, things like bib table lookup still, you know, I cut it down, but it's still 140 nanoseconds. So a per packet cost of 140 nanoseconds still blocks us from being able to do 10 gigabit line rate. And that's, you know, the ultimate goal in all of this is to try to do 10 gigabit line rate on a single core. I don't know if it's possible, but we're going to try our best to see what we can do to get there. So I think that is all. Yep. And so, like Dan mentioned earlier, Rashid's team's hiring. So if anyone's interested in helping with the project, you know, we can always use the extra help. So let's see. Anything else? Yep. That's pretty much all I had. So questions? Yep.
What kinds of tools are you using for measuring all these timings?
Usually ends up being a mixture of things. Perf is the default go-to for a lot of this, because you typically know how fast the packet's moving. So if you run perf on the system, it'll give you a percentage. So if you just do a little bit of math, it's, you know, your packet rate, or was it 1 second divided by your packet rate times your percentage gives you a rough estimate in terms of how many nanoseconds. And then if you want to take it further, you can use things like K-probes. Get in there and just try to record times before and after a certain event. Yes?
You did the measurements on x86 only?
Yeah, I was only working on x86. That's the only equipment I have to work with right now.
Any idea what will happen with your times on 390 or ARM or something?
It's going to vary. So there's going to be gains. I can't say how much, because honestly, most of the work has been simplification. So For example, on like PowerPC, when I put in the DMA RMB, it took things from sync down to LW sync, which ends up being a less expensive barrier, so things should be faster, but I can't say by how much. Same thing for FibTree. I removed a lot of code, so it's just the fact that I'm executing less code is one of the big reasons why that's so much faster. So it's not like I optimized specifically for x86, but yeah, I don't have any idea what the gains will be on other architectures.
So you are mostly targeting x86.
Yeah. Right now, our main target is to try to catch up or beat DPDK for a lot of that stuff. And so it's a lot of trying to figure out what tricks they've been using and okay, what can we incorporate without completely violating the kernel, and so that's how we come up with things like the XMIT more approach to transmits.
Have you tested the waters what means this actually upstream?
Have I tested what's been submitted upstream?
Yeah, I mean,
Yeah, well, all of my numbers are against upstream right now. So Dave Miller's NetNext, all that stuff's in there now. Yeah. Yep. So half the FibTree stuff's there, not all the FibTree stuff yet. So the 140 nanoseconds FibTree, that's there. The 97 or 90 something nanoseconds, which is the version that I'm still trying to clean up because there's a couple RCU issues I have to sort out. I should hopefully be pushing that for the next NetNext tree, so hopefully in like a couple of weeks.
so this is very welcome, I guess.
Yep. Yeah, when I pushed the FibTree stuff to Dave Miller, it was actually kind of surprising to see Dave Miller like, yes, it's about time somebody got to this. It's like, whoa, is this Dave? So then again, I guess they legalized pot in Washington, so maybe. Yep, thanks. Yes?
Do you use crossover cables, or is your switch capable of keeping up with the...
Right now I'm just running back to back. Most of my testing is actually within the same system, so I'm running two VMs. One VM's my transmitter, one VM's my receiver.
Okay.
And so right now I'm just focusing on single CPU, but at the same time trying to make sure any changes I make will scale with multiple CPUs.
Because network vendors define the line rate differently.
Yeah. I used
Just marketing numbers and...
That's the thing is...
Those small packets, everything melts away.
Yeah. Lots of things. I used to work for one of those hardware vendors up until October. I was working for Intel doing performance stuff, so... Yeah, 128 byte small packets for some stuff. Yeah. Yes.
What about those generic receive offloads and segmentation offloads? I thought we are already using them to batch incoming packets
We are.
and to route them at once.
We are, but that only applies to TCP. That's where... So TCP, you can coalesce the flow, but UDP and such gets much trickier in terms of coalescing, because a lot of applications expect their packets to come in the same way they transmitted them, so you can't normally just coalesce frames without having side effects. Whereas TCP, you can usually get away with, okay, I'll coalesce this flow. So large TCP flows, yeah. That was kind of mentioned in the first slide. Not a problem. Large TCP flows get aggregated and then segmented on the transmit. So those numbers look really good. But yeah, as soon as you start getting into small packets like UDP or SCTP, that's where we start seeing these performance problems and have to start dealing with the per packet costs.
Okay, but this might be also used to UDP strings.
Right, but the problem is it's going to be a matter of trying to figure out where we can do it without causing damage. Because for a UDP flow, for instance, it's not uncommon for someone to write kind of a lazy setup where they expect the frame to come in the exact format that they transmitted without extra bytes getting added to the end. And so it just depends. We're looking into what can be done there, but right now, yeah, we'll try to figure out how we can extend GRO to cover more protocols, but it's going to take time. So you don't want to violate any of the protocol specifications and such, which even GRO did a little bit. We have to figure out where that fudge factor lies. Yes?
So in the last slide, the build SKD optimization that you spoke about.
Yep.
So I'm just wondering, is it related to reducing the size of the escape out structure or something else?
Pretty much anything we can do to make that go faster, because build SKB ends up being really expensive. So it's 20 nanoseconds because there's A, a lot of memory there, and B, because we have to initialize it all. So either if we can get away with lazy initialization and put off the initialization until maybe we hand it to the socket or device, or if we can just shrink it down so that we don't have to initialize, on 64-bit, I think it's over 192 bytes, but not quite 256. it's somewhere in that range. It's like 3.5 cache lines. So if we can get it smaller, that's good. If we can get it to go away, that's good. If we can get away with not initializing it, that'd be good. But yeah, we're just trying to see what we can do to get away with trying to make that a lot less expensive. So, any other questions?
You have to ask about this search, why don't you use a hash table instead?
What's that?
Why don't you use hash table instead of this?
In FibTree?
FibTree, yeah.
Because FibTree is actually faster than a hash table would be for this scenario. Because the problem is, it used to be a hash table, and we got rid of it because the problem is it's non-deterministic. Once we start getting large sets, you would have to have a very large hash table in order to handle it. And so in the case of like BGP routes, you can get thousands and thousands of addresses queued up on one routing table. And yeah. And so they did away with the routing hash table and replaced it with FibTree. It's just when they did it, they didn't have the optimized FibTree. So now this is the optimized FibTree, which cuts it down that much further. But that's the thing is, for 64-byte packets, anything ends up being a tripping point. And so that's kind of why I decided to go ahead and take care of that. Because that at least makes it so our timings are much more deterministic. We don't have this, okay, you're at this end of the tree, now you're going to suffer 1 millisecond, now you're at this end of the tree. Okay, maybe 100 nanoseconds kind of thing. It's now much more in line with just, okay, you're about 100 nanoseconds anywhere you're accessing in a large tree. Because that's the thing. It's also my numbers for the FibTree are kind of a worst case scenario. For standard lookup, it's like maybe, probably like somewhere between 20 to 50 nanoseconds. Yes?
Any caching of those lookup results? I think they used to be for IB version 4.
Yeah. Yeah, that was removed, and this FibTree more or less took over for a lot of that. So
Currently no.
yeah, there's no caching. I don't know if there'd be that much gain in reality for caching it either. So for the most part, you might. It depends on the size of the tree as to whether or not you'd see much gain from caching. So it's something I could look into. It's just since it was removed, I'd probably have a hard time convincing people to put a routing cache back in anyway. And caching historically has had issues anyway with, because you usually have to do RCU freeze and whatnot, which means you have to have, a slot available for that. And there's ways you can get RCU to not free things up ever if you pound the system hard enough.
So I think the problem is a big tree, but a big tree.
Yeah.
Just need to go down.
Right. And that's the thing is, there's other tricks we might be able to get away with too. Like, if we want to consume a little bit more memory, we might make the tree nodes larger, so then the tree isn't as deep. There's certain situations we can get away with that. Some of the stuff I did is actually cleaned out a bunch of cruft in the code where it's like, oh, we won't expand unless we have specifically these cases. And it's like, some of them didn't make sense, so I pulled those out. Any other questions? Okay, so I think that's it. And they'll drop.